EC 111, Lecture 11, Set 4. We just want to summarize once more the properties of the secure hash function and talk about a couple of applications so you can see where these properties can be used. So now I want to, I've pre-written some of the properties that we just discussed of secure hash, and that would kind of give us some example of what these can do. The first property is, of course, uniqueness. So we want this to be unique, and this has to be satisfied by the hash algorithm. It also has to be deterministic. You don't want to hash to a different value every time you run the hash function. So this is another very important property. The other thing is it should be kind of a one-way function if it's a secure hash. So that means that if you have the output, it should be really hard to compute the input. And this is basically kind of the one-wayness property that we rely on. Then given one hash output, it should be able to find another value with the same hash. And in the hashing algorithm language, this is often called the one-wayness is often called pre-image resistance. And this other one, which when you have a hash value, it's hard to find another value that hashes to the same hash, is called the second order or pre-image resistance. Now there is another value which is another property which is often the hardest one to satisfy, and that's called the collision property. In this one, we don't care about the value, the exact value of the output, but you want to find any two values that hash to the same value, and this is called the collision resistance. So you don't want that somebody will be able to find that, because then they may be able to use it in some sort of an attack. And then the other property, which is also a property of the security, is that every time you change something in the input of the hash, you want at least 50% property, so every output of the hash function changes. This will make sure that, if you have two things that in plain text hash to the same, are very similar in terms of distance, they hash to very different values in the output hash, and this is called often the avalanche property. Now, these are the desired properties of a hash. In reality, what happens is that these properties will enable us to do many functions, and I'm just going to talk about a couple here. But one thing that you need to know when you're designing these algorithms is very important, is that the algorithms such as hash, one of the most important things about them is efficiency. So efficiency has multiple meaning. One of the ways we want the hash algorithms to be efficient is that you always make sure that it hashes to a fixed size value. So it's a fixed sized output. So that's kind of one version of efficiency. The other thing is you want to make sure that you could run these fast, because you use hashing algorithm in many places in real life. So you want the hashing algorithm to be efficient in terms of, hardware and software implementation. And this is something that, we actually will look at into the project. That's why writing an FPGA hardware accelerator makes sense for your hash algorithm. One thing to know is that the design of a hash algorithm is much more an art than science. So when we go through the hash algorithm that we will be describing for the project, it's not that there is a mathematical one mathematical concept that it's following and it's going through. You will see that there is a lot of steps that these are basically, it's just like if somebody gives you a deck of cards and you're shuffling it. If someone knows how to shuffle well, they most likely do a good job. After a while, they can shuffle things well, so you can't really go back, or you cannot have like an order in the cards. But in reality, it's just not like a deterministic recipe that does that. What happens in particular for the design of hash functions, every time there's a competition, there are multiple entries, and people who are designing these are people who have experience designing kind of hard functions that are not reversible, and it becomes at some point more of art than science. A lot of the entries, for example, to the latest SHA algorithm development, which was approved like 4 or 5 years ago, which is SHA-3, is most of the entries that made it to the final, they didn't have security breaches. They satisfied all these properties, and the one that made it to the final was really the one that had the best performance in terms of hardware and software optimization and performance. So efficiency becomes a really big deal when we design hash functions. One of the applications of a hash function is verifying integrity. This is not even security. This is just to make sure that when you send something, and somebody is receiving it, they've received the original value. It's just like if you put a signature underneath something, and they can verify the signature later on, saying that this was exactly what I should have received. Now assume that some big firm is sending a good file, say a software update, to a user, and with that it also publishes in an open environment that everyone has access to, the hash of that file. Now what happens is that as the user is downloading this patch or the software update, they will also go to this public place where the integrity verification files reside, and everybody knows about it, and they're going to check what they're downloading. Is the signature agreeing with what should have been received? Now, the scenario for the disintegrity is if the virus is sending a bad file, they wouldn't have been able to find the hash to put in that public place, say a New York Times of the hash table values, to also verify the same integrity level. Another really important application which often takes place is authentication. So now Alice is sending something on the channel, and she wants to make sure that nobody modifies the message in transit. So in addition to the message, she's going to also send a hash of this message. And now, if you don't if you don't have, and then you oftentimes even put it in a secret, put in a secret there. So if you have secret or like a key to that, then you would be able to verify this. But if you don't know the secret, you wouldn't be able to verify and authenticate that what Alice was sending is not modified. So this is yet another application of hashing. And if you look around and even search for applications of hashing, you will see several important applications that we have today by hashing. In the next set of slides, we will see the algorithmic design of a hash function, which is popular and which we will be using for the project in this class, namely SHA-256.